Now, so again, output of your decoder and this similarity measure. And you really define this for pairwise relations that exist in your graph. So you're gonna do a sum over all loss functions over different edges in the graph, and you want to see these pairwise relations are preserved or not. So it takes two basically values, and it gives you basically a single value, which is your two real values, and it's going to give you a measure that is your loss, how basically far you are from the target. So we have multiple approaches to learn these embeddings. They fall in general into two categories. They're either deterministic or stochastic. And today we're just going to focus on the deterministic approaches. For that, we're going to categorize this based off of the type of decoder that we're going to deal with. And then this decoder can be either distance-based, as we basically mentioned, or it can be something based off of outer product of two embedding matrices, which is gonna, it is just inner product of two representation vectors for two nodes. And then we have basically probabilistic functions decoders that have their own class. We will see it later. Now, let's have a few minutes rest and we will start from this.
I have a question. So when you talk about deterministic networks,
what was that?
Like when you talk about deterministic network, like encoder, decoder, what's the role of objective function? Is there anything to be optimized if it is deterministic?
It is. So your encoder parameter, as I said, is directly your embedding.
Also the matrix, the Z matrix.
That will directly learn Z as the parameter for the encoder.
Also, it's deterministic because. So what's the word deterministic here? Because then we have.
Oh, you will see. So, for instance, we are using matrix factorization to solve. So I will write them down, and you will see that they will just at the end of the day come down to some matrix factorization of some similarity measure. Yes. Yes, that we will see. Yes, yes. So you will, at the end of the day, I mean, even like, for example, random walks procedures are not deterministic, but it has been shown that you can, at the end of the day, make that basically rewrite that as a matrix factorization problem. So even that can be written in basic matrix factorization basically form. So yeah, that's what we refer to as deterministic.
So it's not a procedure, like it's not, we will be using some gradient descent methods.
It is not. I mean, you can use, but we are not. Yeah.
Like what they are doing now is not that hard. And do we mean like when we say deterministic, does that mean like we will know how error will drop with respect to that, like as compared to like when we think of neural network, we never know how long.
Can you repeat? I didn't
So like so when we think of neural networks or something like this,
yes.
We never know like how loss will drop with time, right?
How
the loss will drop with time, with epoch, sorry.
Okay.
But when you say deterministic, does that mean like we will also know how the loss of the error will drop with every iteration?
We're not gonna do iterations, as I said. So I will write this down, and you will see that just you can use, for example, some singular value decomposition to find your embeddings. So at the end of the day, so I give you a matrix, and you know what your solution is without iterating, without any training or anything. I know you have a background, probably that's why you're trying to connect it with that. So if someone has no idea what these are, it would be basically a fresh mind, easier to understand.
Zara has one paper on her relationship.
If you actually use some geometric deep learning, it's not suitable for the person.
因为就是因为你表包直接用这个他们两个都在要
When we use this technology to run
Okay.
We have a student out. There's someone out.
Yes.
Right, we'll wait another minute.
Some commercial.
Make sure that the deadline for the proposal are they actually extended to
Tuesday, wasn't it on Thursday this week?
now it's Tuesday next week?
So no, it was Thursday this week.
Yeah.
Now it's Tuesday next week.
Yeah, so next Tuesday.
Yes.
Tuesday.
Yes, yes. I thought I did a mistake, so it's extending, yeah. So just to be clear, everyone on Zoom as well, the deadline for proposals was extended to Tuesday, so to accommodate you guys. Alright. Alright, so okay, so we start from Laplacian embedding. Another name for this is spectral, basically embedding, and this and the next basically item that we will review come from classical manifold learning approaches. So the idea behind this is that the underlying basically space of some data, the underlying representation lies on a manifold, which is locally, for instance, it's Euclidean locally, so we can find the distances, measure the distances between these two in Euclidean distance. And for instance, you might have seen these images that, it's interpolating from some bed into some chair or from someone's face to another face, that, they learn to embedding for two pictures and then interpolate in that feature space between these two embeddings for those nodes, and then they project it back from, interpolating between those two in the feature space. So that's basically the idea with manifold learning, and these are classical methods. So Laplacian eigenmap is trying to minimize a distance between data points and their neighbors in their feature space. So you can write this as this objective function. You can say that I have a distance, and let's say that is Euclidean distance between two basically feature representations. And for all basically neighbors, I want to minimize this. If two nodes are neighbors, I want to write a loss function that minimizes this distance. So what happens now, for instance, if two nodes are neighbor and the distance between their between their feature representations is high, what happens is that we will basically get a higher loss, so we will be penalized for that scenario. Now, we have right? So let's write that and let's formulate that as an encoder-decoder problem. We said that we have some decoder that takes two embedding vectors and turns them into some basically reconstruction measure. And here we can see that we have this distance here, so we can think about this as our reconstructed measure, which shows that with S hat, and that's gonna be the output for my decoder, right? So I can assume that there's a decoding function that takes these to Zi and Zj, and it returns to the L2 distance squared. And then I can plug this reconstructed measure here, and I can formulate my loss function as a function of the reconstructed objective and some similarity measure of my choice, right? In this scenario, you can see I have A, so it's gonna be my adjacency matrix here. Now let's reformulate this, rewrite this distance. We can write this, we can find basically open this, expand this, and this square roots will cancel this square here, and then we are left with some quadratic basically forms. We have Zi1 squared plus minus Zj plus Zj1 squared minus Zi1 Zj1 times 2. And we will have that for everything in this relation. Then I can basically arrange this so that I have all Zi squares next to each other and all Zj squares next to each other. And then I have the Zi1, Zj1, and so on next to each other again. And I can rewrite this as basically in some matrix format again. And this one is just the norm of this vector squared, right? L2 norm of the squared. And this is L2 norm of Zj squared, right? So, and this one is just minus 2 times the inner product of Zi and Zj, right? So now I have this, and I plug that back into our loss, right? I rewrote this over here, right? And I plug that back into our loss function. So I have this relation now. I take Aij in, I have 3 sums now. And if you note, I again have sums over some columns and essentially rows of the adjacency matrix, which is gonna give me the degree for the corresponding node, right? So I basically cancel it. I mean, I combine this sum, I write the solution for this sum, it's gonna just be Di. I take this time sigma I, Aij is gonna just be Dj, and then this is the form that I'm left with. Now I can take this back into a matrix format, and I can write this as ZTDZ, where D is just basically a matrix, a diagonal matrix that has all the degrees on it. And I can write this other one as Z, basically ZTAZ. That it is just Z is just our vectors, different vectors of embeddings stacked together. It's all basically nodes together, making a D by V matrix. And then we have ZTZ basically in both of these terms. We have 2 in both of these terms. And we factor these Z's out, and we're just gonna be left with D minus A, where D minus A is gonna give us our, yes, louder. Laplacian, yes. So we are basically rewriting our minimization problem in terms of some Laplacian equation, right? So it's a function of the basically Laplacian of the graph. Now we can reformulate our problem as minimizing this objective function now, where we set 2 constraints essentially. One is in order to, our eigenvectors can have some variable, some random scalar multiplied by them. So we set the second essentially constraint in order to get rid of that variability. And then we have the first constraint, that is gonna get rid of, as we mentioned last time, the eigenvectors that correspond to 0 eigenvalues. So this now is gonna be close to the problem. It's essentially very similar to the problem that we discussed in the clustering, right? We discussed about the approach that we were using k-means clustering for clustering different nodes, right? So we were solving eigendecomposition of some node, and then we were selecting, let's say, last k, basically dimensions of the eigenvectors minus the last one, the ones at least that were corresponding to zero eigenvalues. Now, at least one of them is corresponding to 0 eigenvalue. We showed that Laplacian matrix has at least one 0 eigenvalue. It is positive, semi-definite. So what happens now is that I'm taking a d-dimensional representation of nodes. So I don't have the number of clusters. It's not clustering, but I want to find a d-dimensional representation of that molecule. I'm sorry, that node. And I'm just selecting that the last dimensions that correspond to non-zero eigenvectors from the matrix of eigenvectors. So that's going to be a solution for this Laplacian eigenmap problem, and that's going to give us the essential embeddings for different nodes in our graph. We basically started our formulation with adjacency matrix, but we can really use anything else as well, as long as it preserves the properties of our Laplacian. So as long as we can, do these derivations based off of that function as well, we're safe to start with any similarity matrix. And I'm just to refresh your mind, I'm talking about this A that we plug in as our similarity measure that we wanted to reconstruct. This can be anything based as long as it follows that those properties. A second method is multi-dimensional scaling, again, coming from manifold learning. It's a classical method. The idea here is that we have some nodes and we have learned some node embeddings. And what we want to do is to preserve the distances between two nodes. So if two nodes are distant, it means that they're dissimilar from each other. So we are basically writing our reconstruction objective as some measure of dissimilarity between different nodes. And for instance, one of them can be, any basically user-defined function. One of them can be shortest path, for instance. Let's say that I have these two nodes, Vj and Vk. The distance between these are 3, right? It's the length of the shortest path between these. There is no shorter path that you can take from Vj to Vk that has less than 3, basically length less than 3. So you need to at least traverse 3 edges to get from Vj to Vk. And then you can see that Vj and Vi are neighbors, right? So what we want to do here is that we want to embed this into some basically latent representation, latent space. And then we have our Vk, let's say that it falls into point Zk. We map Vi to Zi and we map Vj to Zj. What we want to do is that if Zj and Zk are dissimilar, we want to preserve this basically their distance in this latent representation. And if Vi and Vj are closer, we want to, again, preserve this. So we formulate this as following. We say that we need, again, in terms of our encoder decoder framework, we have some encoder, which is, we talked that everything is just shallow embeddings. So we need to define our decoder, similarity, and our loss function. So as far as the similarity goes, we are trying to find some measure of dissimilarity, which, for example, shortest path between them, anything proportional to the shortened, basically, distance between two nodes is fine. And then let's say that we reconstruct this dissimilarities, And we use some basically Frobenius norm to find the basically dissimilarity between your reconstructed measure of dissimilarities and your input measure of dissimilarities. And Frobenius norm is just the sum of the squares of all elements, square root of that. So we have that, and we have a decoder FD, which we formulate that as the distance between two, because that's what we want to preserve, the distances. So we plug that into our problem, and that's basically what we basically solve. Now, so far, what we looked at was the idea behind that was that my data has a latent representation on a Euclidean space. But that's not always the scenario. That's not always the case. In some cases, what happens is that you have some basically type of graph, let's say some hierarchical graph, like a tree, that basically you want it can be better represented on some other space. So let's say that on a hyperbolic space, you can preserve these basically hierarchical embeddings. And for that, what we really need to do is to use the measure of distance that corresponds to the basically distances between embeddings in that hyperbolic space. So that there's a model called Poincare basically a ball, hyperbolic ball, and then in that space, so you think that you're basically you are basically considering that as the space of your feature representations, and then you use a distance defined on that space to basically find how similar or dissimilar two different embeddings are, and you define some loss function corresponding to that to basically solve your encoder-decoder approach. Yeah, so all right, so far we discussed about methodologies that are based on the distance, right? So now we're looking at some that are based off of outer product. So the first measure is graph factorization. What happens here is that you have two feature representations, Zi and Zj. You find these are two vectors, d-dimensional vectors. To find the similarity between these, you just compute their dot product, right? Their dot product will give you a measure of similarity between these two. So I defined my basically reconstructed basically matrix as S basically S hat, and every element on this is just the inner product of the corresponding embeddings for the corresponding nodes. So, and that's going to be my decoder. And in index notation, this is going to be written in an outer product of the two corresponding matrices, Z and ZT. They're essentially the same thing, right? And then we need to define some loss function that measures how far are we from our basically goal, and to refine that in order to be able to reconstruct our similarity measure. So we have a similarity measure S, and we have a reconstructed output of the decoder. We call that S hat. And then we sum over, there should be an L here. That's fine, it's just this. So we sum over all the edges, and we find basically the basically square root of the space between these two. Now, this can be written in, so we said that we are summing over all the edges in the graph. We can rewrite that as summing over two sums over all the nodes in the graph. And condition two, we introducing the adjacency matrix into our relation. So now, if two nodes are disconnected, it's going to be the base corresponding element on the adjacency matrix is going to be 0. And then this sum will cancel out for those terms. So it is exactly representing just summing over all the edges. Now, I can rewrite this in matrix format. I can write it as a Frobenius norm. And here you can see, this guy over here is just a element-wise product between this matrix of S minus S hat and the adjacency matrix that you have. And then you can see your problem comes down to approximating some factorization for your similarity matrix. So, and that's because you can consider, if you want to minimize this, you can say that, you know, these two are equal to each other approximately. And that means that your S hat was the outer product of your embeddings, right? So now we say that this ZZT is gonna be approximately equal to our similarity measure. So finding these embeddings using graph factorization comes down to just factorizing this using some approach like SVD to find matrix Z. So another approach is called GRAREP. The basic idea behind this is that the motivation to start this was that, you know, you have some graph, let's say that it is directed graph, and then we talked about